screen I'd like to share. Cool. I do believe you should see my slides now, and we are good to go. Cool. Hello, everyone. So I'm Adam Furmanek. I'm currently living in Seattle in Washington, United States, and today we will be talking about internals of async just a bit. And the whole idea, everything we are going to discuss today will be going around, or will be actually focusing on this one counterintuitive fact that the whole asynchronous programming in .NET and in any other technology is about having no thread for running the task. So I generally assume you more or less do understand how async await work, that you need to put async here, await there, and all these things they do spin up and work together. However, today we are going to see how it's possible that even though we have no thread, we can still get the job done. And we will see how async was implemented in C#, which also influenced plenty other technologies around, because it influenced Java, or actually is influencing Java now. It influenced Rust, JavaScript, and a couple more. So it is something which was really a deal breaker in the last decade. So yeah, let's begin. Let's see how it works. Couple words about me before we begin. About 10 years of experience, back-end, front-end, machine learning, mobile systems, anything around that. Blogger and public speaker, feel free to drop me a line on email or Twitter, whatever works for you. Feel free to take a look at my blog, where I blog about things, mostly about .NET internals or system internals, maths, some algorithmics, all this stuff, which are typically considered computer science. Also an author of .NET Internals Cookbook. If you like reading or learning about the internals of the .NET platform, feel free to take a look at this book. Yeah, that's it. As it was previously said, I'm happy to take all your questions during the presentation. Don't need to wait until the very end. It will be actually easier to cover them as we go through, so we don't lose anything. And let's go. What we are going to do. So our ultimate goal for today is to understand how async and await work in .NET platform, or technically in C# platform. We will understand that this is purely a C# context. It's not something implemented by the .NET itself. It's also something which can be easily translated to other languages and to other platforms, because it's based on a couple principles which we already had in the language and in the platform way before the async and await. So we want to understand all these things, and we want to learn when or where they fail. We want to see how easy it is to generate a deadlock or to break all that machinery if we use it incorrectly. But ultimately, we would like to see how to use it for greater good. So for instance, for awaiting async void methods, that will be our final demo, which will show all the knowledge we learned today. But before getting to that, we need to understand the primitives under the hood, because it's all based on some building blocks available for us since the .NET 1 or since the operating system, from the operating system. So we need to see how they work together and how they are utilized by the .NET platform. Then we'll go through some task details. Probably you understand the task is the bread and butter of the async and await mechanism. So we'll see all the quirks and all the fancy internals of the implementation. And then we'll move on to the second more important, or the most important part of async and await, which is synchronization context. Ultimately, we'll just see how the compiler transforms our code, and then we'll do some magic with deadlocks, with exceptions, with issues, and with awaiting and sync void. Let's move on then. So primitives under the hood. So we start with a native thread. While it sounds obvious, there must be some thread under the hood. It's worth understanding that threads, they are generally heavy because they have a lot of things with them. So first, there are two different types of threads. There are threads which are foreground or background, meaning the foreground threads, they do keep the application alive. As long as we do have at least one foreground thread, the application will continue running. But the moment the last foreground thread dies, all the other background threads can be killed anytime by the operating system, and the application can be terminated. There are so many different metadata structures explaining or describing the thread. There is thread kernel object maintained by the kernel. There are like thread environment blocks. There are stacks, multiple of them, many of them, because we have at least one stack for kernel mode, at least one stack for user mode, and we may have more stacks in each of this area. And it's worth remembering that every stack by default on Windows consumes 1 megabyte of memory. This is for native threads, not for .NET threads yet. However, for each native thread which we create, it by default automatically starts consuming 1 megabyte of memory. And it's more worth remembering that because it's a very interesting case, how many threads does a notepad have? So let's see something simple this time. So let's start a simple Notepad application. So what? So Windows Run, Notepad, brand new Notepad here. And let's now see how many threads it has. So I'm using Windows Process Explorer to open the Notepad. And if we go to the threads, we can see that right after starting the Notepad, like the brand new instance, it has 7 threads initially. That's quite a lot, at least for a brand new application. However, when we start opening a file, so when I hit Control-O and start opening something, you can see that this number increased significantly to 16. So just by doing that, we already have 16 threads. In theory, each of them could be consuming like 1 megabyte of memory. This is not necessarily true for some of these threads because they are used purely for loading the resources. However, this is important because they do occupy the memory. They are heavy. And the most important part about threads, native threads, is that they are scheduled by the operating system, by the kernel mode, meaning that every single time we would like to schedule something, reschedule something, or change the order of the tasks or what we execute, the operating system must be involved. And because operating system or the transition from user mode to kernel mode is very expensive, it makes using thousands of threads not very effective, or maybe very time consuming and memory consuming. As a trivia for you, you may figure out, or you may check how many threads there are running currently on your machine. On mine, it's typically around 3,000 threads. So imagine how much of a memory it is just by creating all of them. And on top of the native thread, there is a managed thread. So managed thread is a thread supported by the .NET platform. So .NET wraps the native one with a thin wrapper, which provides a couple more things to manage the threading and the scheduling. Important thing is each .NET thread can have a name. Native threads, they also can have a name, but it's much harder for them. But for managed threads, it's super easy to set a name, which we should always do. Whenever we do create a new thread manually, always set a name. Why? That is because the name shows us the purpose of the thread, what it's supposed to be doing. It's very helpful when we start dumping the memory and reading memory dumps, because we not only see what the thread is actually doing, but also what it is supposed to be doing. And the thing is, these two do not necessarily align when we investigate bugs. Also, .NET thread or managed thread, it has a managed ID, which is different from the native ID. The thing here is that one managed thread on .NET can be, in theory, executed by multiple native threads. So it can switch between native threads. This typically does not happen. .NET is not implemented in this way, but the specification allows for doing so. And this may be more interesting when we start experimenting with user mode threads, like fibers on Windows or some other libraries providing this functionality. So then the thread can actually migrate between different contexts. So that's why it's always important to remember that the managed thread ID is different from the native thread ID. And whenever you actually log something to your log files or whatever, it's best to include both of these IDs to easily identify the thread in the memory dump or in whatever else. Also, it is only pre-commit stack when it's created, but it reserves the memory, so it does not necessarily consumes the 1 megabyte. It may guarantee that the memory is available, but does not necessarily consumes it. And also an exception, unhandled exceptions on .NET threads. They do kill the application in most of the cases, meaning that whenever you create a new thread, you should always have try catch. This is actually a much bigger issue, and I recommend taking a look at my other talk, which is called Internals of Exceptions, where I cover a lot of these quirks and greedy details. But just as a rule of thumb, remember that always try catch all the exceptions on a thread. So okay, so we do have native thread. We do have managed thread. Now comes the thing. What else should we do? Like, we were probably told many times that we should not be creating threads manually. What we should be doing instead, we should be using a thread pool. So there is a thread pool provided by the .NET platform. It's different from Windows API thread pool. The latter is the native one. The .NET thread pool we will be discussing is something provided purely in the user mode by the .NET platform. It is a bit of complex machinery. It supports a couple sophisticated algorithms for work stealing or for leasing or for adding and removing threads when there is a need to do so. There is this climbing hill algorithm which creates like 2 threads a second. So all these details are not necessarily important for us because first, they do change over time, and second, they like the whole idea of the thread pool is that we don't care, that we just use the thread pool, we don't create our custom one. The problem with thread pool is that we cannot create a new instance of it. It's like a static class which is being reused by all the things around. And here comes actually the first issue of the .NET platform or the design, that these things are accessed like by a static accessor. So it's kind of everything we learn or we are told not to do. Do not use statics like this. Do not use static singletons. Use dependency inversion, yada yada. Here, .NET actually works completely the opposite way. So we cannot create our thread pool, but however, during this talk, we will actually need to rebuild a couple of things in .NET platform to await async void methods, and one of them is going to be a thread pool. So this would be the implementation we could use. So this is the simplest thread pool you can imagine, just a blocking collection of actions or of lambdas which we'll be executing, and then we just create new threads, and each thread iterates through this blocking collection, grabs a lambda and executes it, and also it's set as is background to not block the application from exiting. So this is the simple idea of implementation of thread pool. I don't ask you to remember how to implement it, just the opposite. I just want you to remember that yes, we can build our own thread pool. That is all we need. Moving on. So these are the native things under the hood. And before async and await, there were so many different patterns for asynchronous programming. First of them, probably the oldest one, is called asynchronous programming model APM, which you can easily recognize by using these 2 methods, like begin something and end something. So the begin read in this slide returns you something like async result, which allows you to wait for these things, yada yada, and you can call end operation end read to synchronously wait for the action if it wasn't finished yet, or just extract the result if it's possible. So this is the APM. The other pattern we had is called event-based asynchronous pattern, EAP, which we typically use with callbacks. So we did have some background worker, we were adding a new callback to the do work property, and it was being executed under the hood. And all these things were generally nice. They did work, and they are not like something which we should get rid of. The issue we have with them, or like the drawback, is that they decouple the code. They make it much harder to follow like the program flow, because we do have these callbacks here, callbacks there, and there is this begin read, end read, so it's much harder to figure out what is the order of actions, how they execute. So we wanted to have something which would actually encapsulate the idea of asynchronous code into something which we can pass around. And this is how task-based asynchronous pattern, TAP, emerged. So now we introduced a task object, which basically wraps or encompasses the thing to be executed. So we do have a couple methods like task factory start new or task run, which just start or trigger the lambda to be executed. And then we can pass this task around as a first-class citizen in the language. We can attach continuations with we can do plenty of other things. So it's easier, slightly easier to follow how these things work. However, TAP or task-based asynchronous pattern was showing or was exposing to us all the details of how we join the different pieces of code, because we do have this task continue with, we have lambdas everywhere. So while it did work and did support the asynchronous programming, even though we were not using it this way, it was not typically used to do the most important part of the asynchronous programming, which is to not stop the thread. So that's why we came to the async and await thingy, which we wanted to introduce to have a simple or cleaner way to unblock the current thread. So we will see later how it works and what's the point of it. For now, a couple details. Await can be executed on anything awaitable. Actually, we do not need to return task, even though we typically do. So what we can do instead, we can use extension methods to, for instance, await anything. So there is this await on integer demo, which I do have here. And what we are going to do, assuming that, yeah, this is the correct code, you can see that I am awaiting a simple integer here. Right? And this integer, we can await it because we do have an extension method called getAwaiter, which extends the integer and basically calls task delay on it. So you can see that we are printing something and then awaiting the 2 seconds, 2000 milliseconds, which is 2 seconds. And you can see that, yes, it worked. So we can wait on the integer easily. So this is the most important part. The async supports anything awaitable. It's similar to the for instance, for each in C#, which also supports for eaching on anything which supports the duck typing on the interface. So now the awaitable thing is something which returns, which has getAwaiter, which has the following properties like is completed and result, etc. Async, on the other hand, is only an instruction for the compiler to transform the method. So it doesn't add anything on the platform level. It only adds things on the language level. So this is how it works. And we will see that the most important part of async programming is that asynchronous code does not block the operating system level thread. This is important here because it may block other things, not in C#, it doesn't work this way. But if we do call asynchronous code and we block the thread, then we completely miss the point. The whole point of async is to unblock the operating system level thread so it can go and do other things. And async in C# at a glance is implemented as coroutine compiler level transformation due to the async keyword, with service locator for promise orchestration, which is due to the synchronization context, and statically bound promise factories, which is due to the task, or actually this concrete task type which we return from the function. So let's now go through all these three things and see how they work together to provide the async await experience. So first, task details, statically bound promise factories. So generally, we know tasks have been in the language for a long time. However, the tasks which we used with pilling or with typical usage before async and await were different tasks than the tasks we use now, even though they are represented by the same type. So the original tasks were for the CPU-bound operations, for things which were actually calculating something. They did have some code to run. They were used in TPL world. They were used by task factory or constructor or whatever else. And all these things, they were running some code. And we do have some question here. In the demo, task delay didn't make blocking await. Task delay, let's see that demo again. So let's see the code. This task delay, it did make blocking await, or actually the await blocking await, because we do return the task here. So this await is actually waiting on the same awaiter here. So it did make the blocking await, and we have seen that it did stop the thread for for 2 seconds, the thread was awaiting here as expected. Obviously, we did call.wait here, so it wasn't what we typically should be doing. But the whole point is this is the normal await. This is not some black magic or not some thread sleep under the hood. This is the regular normal await going under the hood on the integer type, and we can have this on any type due to extension methods or whatever else, duck typing. Going back, so 2 types of tasks. So the TPL world used CPU-bound tasks, which were actually doing something, calculating something. On the other hand, in async await world, we do use tasks, but they are IO-bound. They are promises. They are only futures showing that something will happen in the future, and we are just waiting for it to happen. We do not calculate something, but we only wait for the signal that is already done. So there are a couple methods which we can use for that, like task from result, task delay, or task yield, or whatever else. But generally, even though it's the same task type, it's completely different use case. We do not want to calculate anything. We only want to wait for a signal that something is already done. And this something does not need to be a calculation. It can be pure waiting, or it can be some IO operation performed by the driver. However, because we use exactly the same type, we also need to go through the same internals of the tasks. So generally, tasks can be in couple states, which are logically in 3 different modes. So first, we create a task, which can be created and waiting for activation. And then we actually have a task which is doing something like running, calculating, doing some magic. So it is potentially going through this state many times. And ultimately, we have a task which is completed in some way, whether it finished correctly or whether it failed. So let's go through all these one by one. So when it comes to task creation, generally, we can create tasks using constructor, and this is something we should be never doing. The idea here was that the .NET authors, they implemented task in this way because we wanted to have this understanding, this notion of wrapping a lambda of some code to execute into an object which we could pass around. So you can create a new task which would be just encompassing or wrapping the code to execute, and we could just pass it around as a task instance. And then how it would be executed or how it would be scheduled could be decided by something completely different. The point is, no one actually used this feature, so it may be super misleading that you need to manually schedule the tasks. So generally, do not use the constructor for the task. What we should do instead is we should just go with the factory methods like task run, task factory start new, or peeling, or whatever else, which not only create the task, but also schedules it using a thing which is called task scheduler. So now how does it work? If we start decompiling the code, we can actually see that the task scheduler it has the, do I have zoom it here? I probably don't have a zoom it, so I cannot zoom the screen. Give me a second. Oops, it's internal, zoom it. Okay, so if we decompile the code, we can see that we do have a method which is called schedule and start. And this method, what it does under the hood, it goes to the thing called task scheduler and calls internal queue tasks. So it uses some task scheduler thingy to do the magic, to do the job for calculating the or for running the tasks. So now the thing how it works is that schedule and start, when it uses the task scheduler, which goes and schedule tasks on threads. And this task scheduler by default in TPR or peeling is backed by the thread pool, by the .NET supported thread pool, so the one which we have seen previously. There are a couple types of queues, etc. Task scheduler is also pretty sophisticated. However, for us, if we were to ever implement our custom task scheduler, the simplest implementation looks like this. So we do have just a context which with blocking collection, and the only thing which we do here is we just put the things on the collection of tasks and execute them. So this is the task scheduler. Again, not to remember how it works, but just to keep in mind that we can re-implement it easily. So once task scheduler schedules the tasks and starts executing it, we would like to join multiple lambdas together and execute more and more code. So this is done with the continue with method. So we go with the continue with, which is pretty pretty nice and supports plenty of various options which we typically do not use. However, they are there, and we can customize how the continuation is being executed in multiple different ways. For instance, we can specify that a given lambda should be executed only when the original task failed or only when there was an exception. We can specify that it should be executed synchronously and a couple other things. So all these things are in the task continue with. However, typically what we do is we just provide a lambda and that's all. And now how it works under the hood, when we start decompiling these things, we can see that there is whenever we create the continuation, it creates a type called standard task continuation, which is then added on the task with this.add task continuation. Now, what the task continuation is? The task continuation is something which will be executed when a method called complete is being called on the task. So we don't need to understand how this complete is being called. It may be because the task has finished executing its code. It may be because some driver came and notified or signaled the application that, hey, it finished the IO operation. It may be that because some time just has passed or something else. But ultimately, this complete method is called under the hood and on the task object, and it triggers this flow for starting and executing the continuation. So when the complete is being called, it does some internal bookkeeping, goes through some stages. The stage 3 is like the stages which we covered previously on the task state. And ultimately, we get to the method finish continuations, which goes to the task continuation and calls run on the task continuation. And our task continuation here is the standard task continuation, the one we created, and it goes and calls the task schedule and start. And this is something which we have already seen, because we have seen that calling start on a task was actually doing this, calling schedule and start. So we have the full cycle now. So it will go to the task scheduler, thread pool, do some magic, start scheduling the job. So you can see how it works. It's relatively simple. We create new task, which goes to task scheduler and then is being scheduled on a thread pool. Then when the task is complete, something calls the complete method, it just goes to another continuation, kicks it in, calling run on the task continuation. And the task continuation here just goes to the task and calls schedule and start, and the full cycle here. Now a couple more questions about tasks. Should we dispose them? Because if you take a look at the definition or the documentation, tasks do implement a disposable. Should we dispose them or should we deallocate them? And the answer is we should not be doing that. That's because in .NET 4, the task could allocate something to manage the synchronization. So it was allocating the wait handle under the hood for synchronization. So we should be deallocating it. However, in .NET 4, if you call dispose on a task, the task was becoming unusable. You could not schedule a continuation on it anymore, so it would throw an exception on you. However, in .NET 4.5, the regular typical flow with continue with does not allocate the wait handle anymore. So in .NET 4, we should not be disposing because we break the task. Starting .NET 4.5, we don't need to dispose because there is nothing to allocate in most of the scenarios. So generally, don't bother with disposing tasks. And if you see it, it's better to remove the code, assuming if you work with some old legacy platform. A couple more properties. There is a task status property, which shows or is typically misleading, because when it says that the is completed property says true, we typically think that the task just succeeded. However, it's also true when the task was canceled or whether it crashed. So just keep in mind that this is completed may not be a good idea. Maybe it's better to just check the task status. For task ID, again, it's like a managed thread ID, some identifier which is completely independent. However, the documentation tells you that it's that there is no ID collision for tasks, and this is not true. You may have duplicate task IDs, so generally do not assume they are unique every single time. That's all when it comes to tasks, and we here face a problem or an issue because tasks are classes. So they are heap-based, so they are deallocated or need to be cleaned up by the garbage collector. However, the problem with GC and with tasks is that once we start with async and await, we have literally tons of them. So GC has a lot of work to do to clean them up. And that's why the thing which was called value task was introduced to provide the same logical concept like the task, only one which is not heap allocated or something which is a structure. So the value task is a structure, so it's passed through the stack, not through the heap. It doesn't go through the GCD allocation, etc. However, using it is a slightly more sophisticated, but we can beat actually even more memory. Feel free to take a look at the put value task source repository in GitHub showing how to do it. Also, there was a very nice research project called Midori, which was operating system in Microsoft, which was providing all the APIs in Midori were async await, all of them. And everything was basically using tasks, and that task in Midori was a structure. And Joe Duffy, who was influencing or impacting the implementation of tasks in .NET, actually regrets the decision to make the task in .NET as a class, not as a structure. But that's a side note. Okay, that would be it when it comes to tasks. Now we get to the second important part of async and await, which is synchronization context. And this is actually more important in async and await world. More important because it leads to so many deadlocks and so many issues, but unfortunately the documentation or when people learn about async and await, what they read is put async here, put await there, it works. Synchronization context is barely mentioned. However, it's all about the synchronization context here, as we'll see. So before synchronization context, we always had in .NET platform, we always had a need to be able to synchronize things, to execute something somewhere, somehow, and just get the result. We do not care how the things are executed. That's the whole point of asynchronous programming. We just want to fire something and forget, trigger it, and at some point, maybe get the result of it. We don't care how it's being technically done. However, to get this result, we had to have something which would be able to access the result, the outcome of the calculations. And initially, it was isynchronize invoke. However, isynchronize invoke interface was tying the threads and the execution code. So whenever we did have isynchronize invoke, we knew it's backed by some specific, very specific thread. It worked for us nicely. However, we do not necessarily care about these threads. We just want to run code somewhere, somehow. And that's how synchronization context appeared. And it's part of a bigger thing, which is called execution context. And it's a bag for holding so many things with the thread, because we do not only execute the code. Thread has permissions, thread has like thread static values, logical context, impersonation, like policy, which code we can execute, and yada yada. There's so many things which we need to be cared with the code we execute. However, now we see the trouble. We run into troubles because if the code which we execute can switch between multiple threads, it also needs to handle the things it carried on the original one, like the impersonation or policies or security. So all these things are encapsulated with the execution context. And also one of the things in the execution context is the synchronization context, which manages the synchronization. The synchronization context class is basically an abstract contract providing a notion of being able to run operation somewhere, somehow, sometime. It does not specify whether it's based on threads or one thread or many of them, whether it's synchronous, asynchronous. It does not specify that it needs to actually do synchronize something. It just gives us the ability to run something. And that's the whole idea, because we don't care about how it's being executed most of the times. This should be taken care of by the platform or by the framework or libraries we use. All we should be doing is we should just drop the things on it so they get calculated, and that's all. We should be good. However, if we do forget or if we do ignore how these things are executed, then we actually may run into issues. So we need to understand the synchronization context is there, and this whole idea of not taking care how things work does not necessarily work. And why is that? That's because whenever we do await the await table type, so whenever we call await something, the current synchronization context is captured, and then the continuation goes through the synchronization context. We can stop this capturing by calling configure await false, and we should be always doing that, and we'll get to that in a sec why. However, the important thing is when you just do await something, you capture the context, and if you do it improperly, then you will hit the deadlocks and other issues super easily. Synchronization context is effectively a global variable. So just like thread pools are global variables and used by static, the same goes here. It's a global variable, and we probably, it immediately rings a bell that probably something's wrong here. There are multiple different implementations of synchronization context, and it can be changed by the thread anytime we wish, and we cannot stop it, we cannot control it. And when it comes to different implementations, they do mostly depend on the type of application we run. So whenever we do run like default, like console application, or when we don't have the synchronization context, the default one which is used, which is supported or backed by the thread pool. So whenever we don't have the synchronization context, the continuation is posted on the thread pool directly. However, and for instance, in desktop applications like WinForms, WPF, whatever, this synchronization context, they do assume that the continuation must be executed on the same thread. Why is that? Because in desktop applications, only one thread is allowed to modify the user controls. Whenever you create buttons, windows, lists, drag and drops, whatever else, they can be modified, they can be touched only by the one and only thread, the UI thread. So if you do await, then the continuation must be executed on the same thread. Otherwise, if it goes to some different thread, it will throw the exception when accessing the UI controls. So that's why the synchronization context for desktop applications needs to be backed by exactly one thread, the UI one. However, similar case is for ASP or web applications. However, there we don't care about the thread. What we do care about is the HTTP or network request we are currently handling. So we would like to be able to execute the continuation in the context of the same request. And whether it's the same thread, we don't care, but it must be the same request. So all the continuations in ASP.NET for given network call are executed synchronously, like one by one. You cannot have multiple continuations going on at the same time, and they will also have the same request. This is interesting because ASP.NET Core changed this and allows now for multiple continuations being in flight at the same time. So if you just like translate or copy the old ASP.NET application to ASP.NET Core, you may introduce parallelism, which wasn't there before, or concurrency, which we do not expect. So this is yet another thing we should keep in mind when it comes to synchronization context and other solutions. That's it. And now we need to see how these two things are tied together and how it's done by the compiler. And this is called a state machine on the compiler level. And this is coroutine compiler level transformation conceptually. What we are going to do is we will start with this simple code to see how the state machine works. So let's start with this method, which is called our async method. And what we have here in this method is we do have the async modifier. What we are going to do is we will see how this thing is being compiled and how it works under the hood. And we can see that we will have like 4 different logical parts divided by the multiple calls to await, right? So we do have 4 logical parts separated by await to different things like await task from result, task delay, yield, and ultimately we throw the exception. So this is what we are going to investigate here and see how these things are being compiled. So the first thing, how do I make it? Like this. So the first thing right after compilation is that whenever we do compile the method, it drops the async modifier. This is the C# code compilation. It's not the just-in-time compilation. It's the C# compiler which drops the async and replaces our method with something like this, something which has plenty of different like types with weird names, like program, our async method, the __1. So we will need to go through all these details, and just to give you a brief idea how big it is, after compilation, our code, which had like 20 lines, currently after compilation, it has something like 130. So it's a plenty of code generated under the hood, and we'll quickly see how these things work. So important things to see immediately after compilation is that we do set some state to -1, that we do call some start method here, and that ultimately we just return from this method. We return the task from this method. This is how we have the task returned as the value of this procedure. So let's see how these things work. We see that we do create some weird type called the __1. And when we decompile it, we can see that it has a couple things. First, it has the integer field called state, which will be used to indicate where we are and how it works. Then it does have the method builder. This is a type helper from the .NET platform to build the async await methods. And then we have 3 different awaiters. You will remember that we had 3 different awaits in the method. First of them was for task from result of Boolean. Then we had for task delay, and ultimately we had for task yield. So you can see all these awaiters being shown here. So this is what we do. So initially, we set the state property, this integer state field, to -1, and we call the start method on the type. And you can see that the start method, what it does under the hood, it calls the method called moveNext. And this is the name which we should remember because it will appear many times through the discussion. So we go call start and immediately call method called moveNext. We do not wait, we do not reschedule, we do not switch threads, we don't do anything like this. We just go and call method moveNext. And this moveNext is actually the method which is the translated version of our code. So what it does is it has 3 things. First, it captures this state variable to the local one, to the local integer called num. Then we have try block, which will execute our code. And then we have a catch exception, which handles the exception immediately, meaning that whenever we start this thing, we actually always handle exceptions. Exceptions are not allowed to escape the method with async modifier, so it changes behavior significantly. So what this try does under the hood is it has these 4 logical parts which we covered previously. So we shown that there were 3 awaits and 4 logical parts. So we also have 3 awaiters here, and we also have 4 logical parts like scrambled in different order to do the magic. So let's see how this goes. So we enter the try block after setting the state to -1. So what we do, you can see that this switch block does not have case for -1 state. So what we do is we just go to the default. And in the default block, what we do is we print the first part. So you can see, even though we called await on this method, even if we call await on this method, we start executing it immediately on the same thread. No context switch, not thread rescheduling, no blocking, nothing like this. We just go execute the code. And then we get the awaiter for task from result, and we check whether the awaiter is completed. And obviously, the whole point of task from result is that the task is already completed. So we do not enter this if, because the awaiter is being completed, and we just carry on. So you can see that even though we did have await task from result, and we do have this await keyword, we do not stop. We do not deschedule, reschedule, do the context switch, nothing like this. We just carry on. So we finished in line 69 here, and then we go to the next line. And you can see that the next part of the code is console write line second part. So we immediately are after first await and we print something, and we get the awaiter for task delay. And this time, when we ask the awaiter, hey, are you done? The awaiter tells us, nope, I'm not done, because that's the whole point of task delay, right? It needs to wait. So what we do is we do some bookkeeping. So we set the state field to 1, we capture the awaiter to some field, and then we call await unsafe uncompleted, and we return. So let's see, what does this await unsafe uncompleted do? So what's it about? So when we go to await unsafe uncompleted, the thing it does is it gets the completion action and then calls awaiter unsafe uncompleted. And the completion action, which we create here, is actually a type called async method builder core move next runner. We have already seen the method move next, so we probably see or assume what this move next will do. And when we dig deeper into this move next, what is happening is it creates the context callback, and ultimately it just calls the move next method, the same method which we are now executing because we started by executing move next, and then we go deeper and deeper. So what happens next? Well, because it's all based on tasks, we need to set this continuation on here on task set continuation for await. So this is super similar to the regular task set continuation, which we have already seen when this dissecting task continue with. And set continuation for await, what it does is it captures the synchronization context. So if we did not specify that we don't want to capture the synchronization context, it is being captured, and the continuation goes on the synchronization context, or if there is none of them, we just go on to the task scheduler. And then we add task continuation the regular way, just like with continue with. What happens next? Ultimately, at some point, the continuation goes and calls the callback on the continuation, and synchronization context, what it does is if we capture the synchronization context, the continuation wrapping our lambda just goes to the synchronization context and calls post method on it. So this is how these things are coupled together. So there are two loops which we are observing now. The first loop was with task, which we've seen. You do start task, it goes, when it finishes doing some work, it goes to the continuation, calls start schedule and start on the continuation. The continuation goes through the thread pool and executes on and on. Here it's similar, however, our continuation, when it's being executed, it goes to the synchronization context and asks the synchronization context to execute the continuation. And now, depending on the implementation of the synchronization context, we'll have different behavior. It may be on the same thread, on different thread, it may do synchronously, asynchronously, a couple other things. Important thing also, if we go back to the code here, is that after calling this await unsafe uncompleted, what we do is we just return. So we immediately return from this function. And if we go in the return back again to the code, to where? Back to here, you can see that after returning from all this machinery, what we do is we just return the task at this point. So you can see that we execute as much of the code as possible. And when we cannot move on because we cannot proceed because the continuation is not yet ready, the awaiter is not yet ready, what we do is we just schedule the machinery to go back through the synchronization context, and we return the task. So there is this promise indicating that something is being going on under the hood. What happens next? When the continuation is finally executed, we did have this move next runner. So the move next runner enters again this move next method. So we, in line 36, we get the state to the local variable with the num field. And then what we do is we enter the try block, we enter the switch, and this time for this task delay, you can see that the state was set to 1. So we enter this case. So we actually, from this point, we jump back in the code execution to here. And what we do is we get the awaiter and then we jump. And this jump is actually jumping back here. But this time, the awaiter is already finished. So when it is finished, we can carry on and we can move on. So we already know it's finished. And when we go to the next part of the code, we can get the value of it if it's needed. The same goes for the next part. So we, after jumping, we finished somewhere around here. We print the third part awaiter. We again call task queue get awaiter. We check if it's completed. If it's not, then we do the same bookkeeping as previously. The only difference between task queue and task delay is that we do have different type of the awaiter. So it's different awaiter here. And then for task queue awaiter, it always schedules the continuation through the continuation context. So it's never possible to go without the rescheduling through the context. And then ultimately, from the awaiter, from the continuation, we go back to the case 2. We check, we get the awaiter when it's done. We use the go to instruction to jump next, etc. So this goes on and on and on, and it's pretty straightforward or pretty repetitive. Ultimately, the last part is basically throwing the exception, which is immediately caught through the try catch spanning the home method, and then this exception is being set on the task object. And what happens next is it depends on the method type. If we do have async task method, the exception just sits there. If it's async void, this exception is being propagated. We'll see that later. A couple more things. State machine is also handled differently. It's suit class in the debugging scenario. However, it's structure in the release implementation. And this is also related to another question which we had in chat, which is, can we use value task with task when all? And all these things are related like to this and to other implementations. We typically would like to go with task as a structure as much as possible to not have the GC being forced to clean things up. We can use value task with task when all. However, the value task will be boxed at that point, because value tasks should be used only in the scenario when we are actually not waiting. Because whenever we need to wait, we actually need to do the boxing. Similar situation is happening here. The more data we actually capture in the async and await, like primitive fields, integers, or whatever else, they also need to be boxed and wrapped and put on the heap and then cleaned up. So to beat this allocation as possible, as much as possible, what we do is we switch to structures where it's applicable. However, we need to keep in mind that structures won't speed things up just like that. They need to be used properly as well. Otherwise, we just get the boxing. Yeah, that would be it for this part. A couple more ideas like async task versus async void. We should always be using async task, never async void. However, async task, it captures the exception, does not propagate it. Async void does propagate it. Yeah, and these things we can safely skip and get to the next part, which is called deadlocks. So we covered the 3 important pieces of the task implementation or the async await implementation. We do have promise factories based on the return type of the task method. So we do have task or standard continuation or whatever else. This is dictated by the type of the type which we return from the method. We do have service locator for orchestration, which is synchronization context, which we capture as a global variable. And we also do have the coroutine transformation, which is basically what we went through with the compiler. Now comes the thing. How do we generate deadlocks, and why it's important to keep in mind all these synchronization context details in mind? So we already mentioned deadlocks. Because there is no thread, we can cause a deadlock with just one thread, and depending on the application type, we may have issues. The rule of thumb is use async all the way up. Always, never wait synchronously on the task by calling .wait or .result. And the other important part is use configure await false all the way down. Why is it so? Because depending on the synchronization context, we may run into issues with the context propagation. So what we are doing here is let's take a simple example and see how the synchronization context is being propagated. So we enter in some desktop application from the button handler. So what happens here is we call await process data async, and we know that await does not schedule the thing. We just start executing the code. So we are on a UI thread at this point, and we enter here, and we are still on the UI thread. So we call something else like download async configure await false. And we have seen that even though we specify await here, it does not mean that we will do any rescheduling. If the download async finishes in a synchronous manner, because the data is already available from the cache or whatever, there will be no scheduling and going through synchronization context or whatever else. So at this point, this continuation, we may not necessarily go through the synchronization context. We may continue on the same thread. However, if there is a need to reschedule, because we did specify configure await false, this continuation will go through the thread pool. Because we do not have synchronization context. So the same goes for the next part. We call transform async, we call configure await false. So this continuation will also go through the synchronization context, and since we didn't capture it, it will go through the thread pool. And then we come back to this part here, and this continuation would like to go through the synchronization context because we did not specify that we don't want to capture it. And since we were on the UI thread at this point, there is a synchronization context, which is the UI synchronization, which will pause and resume this continuation on the UI thread. So it will go and set this continuation to go on the same thread where we started. So even though this piece of code, like where my arrow is, was running on the thread pool or some other thread, the continuation here in the download button click is going to execute on the UI thread. And this may be very dangerous. Why is that? Because if we take the same code, which works in one scenario, it may fail in different place. Let's take the console application here. So we do call some operation on context, and then we call synchronous wait. Okay, operation on context is basically an async task method. So it awaits task delay, and it would like to execute this continuation somewhere. Because we do capture the synchronization context here, the continuation should go through it. But because this is a console application, there is no synchronization context set. So this continuation will just go through the thread pool. So the thread pool has many threads, so it will execute the continuation, and then ultimately this .wait will finish waiting because the continuations are done. However, if we take exactly the same code and move on to the desktop application with the synchronization context, we will get a deadlock. Why is that? Because when we execute this instruction, we block the UI thread using .wait. It's synchronous wait, and the whole point of asynchronous programming is to never block the operating system thread. So then with this continuation, it would like to go through this captured synchronization context. So it would like to go on the UI thread, but UI thread is blocked here at the wait. So we have a deadlock because this continuation, this part here, would like to go to the UI thread, but this .wait method waits on the UI thread for this continuation. So this is how it blocks the application. The solution for this is relatively simple. We can just call configure await here and do not capture the synchronization context, which makes sense, right? The continuation will then go through the thread pool, so the UI thread will be blocked, the application will be frozen for a second or so, but it won't crash the application or it won't stop the application indefinitely. However, it does not solve the issue all the times, because we may also have the continuation, which even though this line will execute on a thread pool, it explicitly wants to go to the UI thread. And because UI thread is once again blocked in here, we cannot do it. We are effectively having a blocked synchronous waiting, so we have a deadlock again. How to fix it in the desktop app? Well, there is a nice hack, which we probably shouldn't be doing, but sometimes we have to. Instead of calling .wait, what we should be doing is, or what we can do, is we can spin a loop and check whether the task is completed. And as long as it's not, we explicitly call do event on the application, and then we sleep for a millisecond. So what is going to happen is when the invoke is being called and this lambda is being posted on the UI thread, it will go to the message loop, which we will execute by explicitly calling application do events. So our UI will be frozen for a second because we have task delay, and then it will be consuming some resources because we will be just doing the busy wait, but at least it will unblock itself after a second. So we can hack these things. However, the whole point is to not have to. The whole point is we should never be calling .wait. We should be calling await to unblock the thread. Is configure await false guaranteed to always not run on the UI thread? It is. The configure await false makes that we do not capture the synchronization context. Because we don't capture the synchronization context, the continuation will be scheduled on the default task scheduler, or actually not on the default, but on the current task scheduler, and we'll see magic around that later. And this task scheduler, by default in .NET, is backed by the thread pool. So the continuation will go to one of the thread pool threads. We could, in theory, change this so the task scheduler would go to the UI thread again, but that would be like a blasphemy. Most people don't do it. So generally, it's 99% safe to say that configure await false will guarantee to not go to the UI thread for us. However, there are a couple more interesting details about that, because configure await is very local. It does not affect the whole continuation, only the local part of the continuation. So if we do get this code, just like here, so what we are going to do now is we do have, again, button click. So here we are on the UI thread. We call get await or get result. So this is basically .result or .wait. So synchronous wait on the thingy. But now we may think, okay, we are synchronously waiting, but then we do the configure await false. So the continuation from here should be executed on the thread pool. And this makes sense. However, we call method wait2, and method wait2 calls await wait3 without specifying configure await false. So even though we did specify configure await false here, and this continuation will go to the thread pool, this continuation from the method wait2 will capture the synchronization context and try to go back to the UI thread. So what happens is in wait3, if we do something like this, that we do task delay, what is happening here is we do block the UI thread at this line. This continuation from here does not capture the synchronization context, so this goes to the thread pool, but here we do capture the synchronization context, so this continuation wants to go to the UI thread, which is blocked here. So we have a deadlock again. So the rule of thumb number 1 is use async all the way up, never wait synchronously for the tasks. Rule of thumb number 2 is use configure await all the way down. You need to use this configure await here, here, and also you should use it here, all the way down. So it's like a cancer spreading through the code base, and it should affect all the parts of it. The third thing, which is interesting here, is that the synchronization context is a global variable. There was a question in the chat. We have been told that there is no synchronization context on .NET Core, and therefore there is no need to use configure await false. What's your suggestion? First, to clarify, there is the synchronization context like by default. The whole machinery, the whole logic is there in .NET Core. The difference is that synchronization context is being used rarely over there. Like ASP.NET Core does not have synchronization context. The console applications don't have synchronization context. But if you do have desktop applications, they will use synchronization context most likely because they need to go through the UI thread. Therefore, there is no need to use configure await false. My rule or my recommendation is whenever you write a library which you do not know where it will be executed, always use configure await false, always. If you do write the code which you know where it's being executed and you can guarantee there is no synchronization context or whatever, then you can skip this configure await false, even though I would recommend put it, always put it. That's because your application probably will live longer than like a month. So in a year, you may not remember that you assume there is no synchronization context. Someone may just introduce it and you have deadlocks. So unfortunately, my rule of thumb is always put configure await false, always, unless you really know what you're doing and you really know it will be safe forever. Is there a way to override behavior so we don't need to write configure await false all the time? There is no. Unfortunately, you need to put configure await false explicitly every single time. There are some hacks to avoid doing that, but generally it's better just to put it. It's the easiest way. This is actually, I do have yet another talk which is called Async, the biggest mistake in C#, in which I go through multiple issues with async await code, and I show how to deal with this configure await issue. Unfortunately, these are hacks. Generally, you need to put it, so every single time you use await, you should be using await yada yada dot configure await false. And yes, I do know it sucks, but this is how it goes. Actually, you can even Google articles like when Microsoft was implementing this thing, they were discussing whether by default it should be capturing the context or should not be. And probably today they would change the behavior, but years ago when they were working on it, well, there are plenty of like desktop applications, and also ASP.NET was using the synchronization context under the hood. So it was just simpler to capture it by default because we still wanted to capture it in some scenarios. So it was easier to not break the code by capturing it by default. However, today we, like the whole .NET platform wants to get rid of it. So it removes it as much as possible, but we still, because we have this legacy code bases or we have this old approach and it's hard to change the default without breaking everything around, we need to call configure await false explicitly. Moving on. So the synchronization context is a global variable. Let's take this unit test, which is written with an unit. What we do here is we do some abomination. So we create a new form in the code, and then we just await task delay, and that's all. What's going to happen here? This thing never finishes. It runs forever. There is yet another question. We'll get to that in a second. Okay, so what happens here? Why does it like deadlocks and never finishes? That's because whenever you call new form from the Windows forms, it goes when it initializes the instance. What it does, it checks whether, hey, is my synchronization context set to the WinForms synchronization context? And if it's not, then it replaces it. So this new form not only creates you a new instance, but also changes synchronization context on the thread. And because the end unit waits on different synchronization context, it doesn't know that this continuation was executed and has finished. How can we fix that? Well, yet another hack, and this is how you change synchronization context. You can get the global variable, and then you can just call static global method, hey, set synchronization context on the context. And this replaces thing. And now you can see, because these two lines of code can be executed by anything in your code base, so anything in your code base can change the context. That's why you should always call configure await false. Otherwise, you hit issues, you have problems. Let's now go back to the question. We know that sync thread sleep is bad within async code, but can you explain exactly why? Also, can you speak to people wrapping sync code with task run, async lambdas, and then cons of doing it that way? Let's start with thread sleep. The whole point of asynchronous programming is to not block the operating system thread. If you do block the operating system thread, you're doing it wrong. by definition, by design. Because why do we want to have the asynchronous code which does not block the thread? Because threads are heavy. We want to have as few threads as possible. So when the thread, instead of it waiting for it to, or for the thread to be waiting, we would like the thread to be doing something else. So we would like to do this message pump logic just like in the UI application, right? We schedule something, we handle the message. When there is another message to handle, we just handle it. Thread sleep explicitly blocks the operating system thread. That is bad. It's the same bad as like doing, I don't know, synchronous writing to the file because it waits, synchronous writing over the socket, synchronous waiting for task wait or whatever else, because we do block operating system thread. We would like to unblock the thread so it can go and see if there is anything else to be done. And if it is, it just gets and does it. That's the whole point. So that's why thread sleep is bad. Can you speak to people wrapping sync code with task run, async lambdas, and the cons of doing it that way? If you need to run synchronous code, that depends on the code. Okay, we'll get to that because there is a follow-up question. Okay, I want to sleep in non-async method. If you do have non-asynchronous code, then your thread is not capable of doing something else when it's waiting, because there needs to be a bit of a machinery under the hood. And this machinery, I'm not showing it here, but you can imagine that how does a thread knows when it's waiting how to do something else? There is a collection of messages or collection of actions to be executed, so it can go grab another message from the queue and start processing it. If your thread is not doing that because it wasn't designed to do so, because it's not the thread capable of doing this, then if you have not asynchronous code, it doesn't matter how you block it, because the thread won't do anything useful anymore anyway. So if you want to sleep in a non-asynchronous method, thread sleep is the way to go. Or you can do anything else. You can block your thread in any way you wish, because even if you do not block it, it doesn't give you a thing. It's not free that the thread will do something else. It's something which needs to be implemented and it needs to be handled. So in non-async code, thread sleep is okay, because waiting in different ways won't give you any benefits. In async code, any thread sleep is bad because it blocks the thread, and the thread could be doing something else. Okay, now coming back to the task run, wrapping synchronous code with task run and cons of doing it that way. That depends on the code, because it's a much bigger question here. What actually is the synchronous code doing? If it's just calculating something, then it's probably not an asynchronous code at all, because asynchronous code is just waiting for something. However, if this synchronous code is actually waiting for something and does busy waiting or whatever else, then task run may have the issues with first, because you create a task run and you wait synchronously, it will just block some other thread. So we would like to avoid blocking any thread at all. And second, if the continuation would like to go back to your synchronization context, etc., then it may cause issues. Otherwise, wrapping synchronous code with task run is actually the way to go, and how we should do it when we need to like start integrating two legacy code bases, or the new code base with the legacy one, and we have to merge them together. So yes, task run is the way to go. And if the question is there anything better? Probably not. Probably task run is the simplest and the most working solution. Okay, I don't see any other questions on the chat. Let's carry on. So we have seen, there is a question. What is the real performance reliability improvement implications of not using await for the last line of some internal method, as long as some outer method will await anyways? I do not know which some internal method you refer to, whether it's from my code bases or just an internal method. I will assume the latter. Of not using await for the last line, the outer method. Okay, if you do not await, it's hard to answer this question without a specific example. If you do await somewhere up in the chain, then you unblock the thread you started with. So this is okay. The question is whether you do block some other thread. If you block some other thread, like from thread pool or whatever else, the implication is that the thread is just waiting, probably waiting idly for something to happen. Otherwise, if we do not block the thread, or if we block it the asynchronous, the await method, then it's okay. We don't need to do it. Okay. So many questions. Okay. What is the real performance reliability test? I answer. Say we have two awaits within the method. We have two awaits with some method. We don't have to use await for the last one. Generally, like I said, with synchronous, with asynchronous code, it's always better to put the async and await all the way up. Hard to answer whether not using the await is going to break something. Generally, it's better to assume it will, but it may be that it's not breaking. This is perfectly fine. It's important to actually understand how these things work, not necessarily blindly following these principles, but generally the rule of thumb is put await all the way up. Moving on to the next question, do you have any ideas how to begin implement async and await approach in legacy ASP.NET MVC project that started before this feature was invented? That is a very good question, and the ultimate answer is you probably can't. If you do not put await all the way up, you will run into deadlocks just the way I'm showing here. And been there, done that. So it's not that I just theorize, I have seen things like this. So generally, you need to do it, like if you want to be safe, you need to have await all the way up. You cannot just do partially here, partially there. It's good if you can, for instance, so you should be probably working on it not horizontally, like through layers, but vertically through features. You get one feature and you re-implement whole part of the flow to be asynchronous. Otherwise, you don't get benefits and you risk deadlocks and your code base is inconsistent. So generally, there are multiple issues. This is actually a big issue and very good question that, hey, whenever you do go with async and await, you need to commit to that fully. You cannot do with it partially. Otherwise, you run into more troubles then, and you may lose all the benefits super easily with like one wait hidden somewhere. So you need to go with it fully. And with legacy code bases, it's just hard. It may be even impossible without like complete rewrite application. Cool. I think I have answered all the questions. If I have missed something, feel free to repost the question. And let's carry on because we have a lot more to cover, so we may probably need to speed up and continue. Task completion source will actually skip because of lack of time, and thread pool starvation as well. We'll get to the exception handlings. So what happens now? Async and await also changes the way we handle exceptions, because void methods, they do propagate exceptions immediately in the out-of-band manner, but task methods, they do capture the exceptions. So now what we are going to do is we are going to see the demo. This we can skip. This we can skip, and we can get to this, to the exception in async. Okay, so what we are going to do here is, let me just find the exceptions where it is. It's here. So what we are doing in this application, you can see that we start with main method, and we call method throw within try catch, and the method throw is async void. It awaits for 300 milliseconds and then throws the exception. So what we could think may happen is, hey, this throw was inside try catch, so the exception which is being thrown should be handled here. Unfortunately, it's not the case. The exception is just being propagated, but you can see that we do have after sleep printed out, and we do have done. So it seemed that it worked. But now let's see what happens if we just add a random delay somewhere in the middle here. So what should happen here, we may think that, hey, because we execute throw and because we are sleeping here, the exception after 300 milliseconds is being thrown when we are inside the try block. So the catch should handle it. Unfortunately, it doesn't work this way. The exception is being printed out. What's more, this part of the code, like after try, after sleep and done, is not being executed at all. The application dies. So you can see just using, adding random sleep somewhere in the middle broke all the things. So generally, with async void, never use async void because handling exceptions is much harder. What we can do, we can switch to async task. And what is happening now, you can see that the Visual Studio shows me that, hey, this method is not awaited. And you can see that there are no exceptions printed out at all. So what is happening is the exception is being thrown and handled or hidden on the task object, which is also not good for us because whenever it's hidden here, we do not know it happened. Until we await things, we do not know it happened. However, there is another thing which is called unobserved task exception. So whenever the garbage collector realizes that, hey, there was an exception thrown on the method and the task was not awaited, what happens is the exception will be propagated using the unobserved task exception on a task scheduler. So you can see I did execute this thing. I am now waiting in console read line. There is no thread, no exception, nothing here. We are just waiting. Once I press enter, the GC collect is being called. So it will find that the task was not awaited and our handler for unobserved task exception is being executed. So you can see that these exceptions are hidden. However, they may be propagated later and they also may crash our application depending on the .NET version. So generally, always have this handler for unobserved task exception, but even better, always await your tasks. Never do fire and forget with async. Always await tasks. Okay. So that was exception in async. Now, when it comes to this, we'll skip because it's mostly about native thingy. There is yet another thing about the exceptions, which changed with async and await, which is namely stacking the exceptions. So before using async and await, when we were going with continue with, what we could do is we could specify that, hey, we would like to create a task which should be attached to parent. So we are not only like running execution one after another, but we could make a tree of the executions of the continuations. So what happens here, if we await a task like this, and this task creates children, what happens is we have only one exception printed out. It happened that it was second exception here. So the one other exception was basically lost. How do we catch that exception? How do we extract it? Well, the answer is what we should be doing is we need to go with OTTPL run to unfolded here. So you can specify that something should be executed unfolded. And this is how we can handle the exception. There are also a couple differences with await versus wait versus getAwaiter.getResult. They mostly go down to the stack traces. So you can see just by looking at like the arrows, they do differ between the different solutions. It's not that important for us. However, we need to keep in mind that exceptions are not compatible with await. They're much different than they were designed to be. Okay, unobserved task exception we convert. And now we get to the last thing which we would like to see. How do we await async void? Seeing all the issues with synchronization context, tasks, deadlocks, and other things. So what we are going to do is we will re-implement a bit of .NET platform to do this magic. So what we are doing in this code base is we do have a method which is async void, which awaits for a sec and then throws the exception. How we are going to do it is we start by implementing custom task scheduler, which has the collection of tasks and which just executes them one by one. Then we implement custom synchronization context, which creates task scheduler like custom task scheduler, and which creates custom task factory, which hides the .NET scheduler and uses our custom one. And then we post things using our factory and our scheduler. Ultimately, we also count the operations to know how many operations are in flight. And what we do is we provide a helper run method, which what it does is it goes to task run, replaces the synchronization context on a thread, gets the factory and goes through all the tasks which are on the factory and executes them one by one in line 94, and then waits for them in line 95. So whenever a continuation is being scheduled, it will go through our custom synchronization context, custom task scheduler, and custom task factory. So we will ultimately handle it here and be able to execute them one by one. And ultimately, what we do from this method, we just return from the task run. So the only thing we have here is the task, and we can wait for this task using regular .wait or await or whatever else. So the way we run our method, async void method throwing exception, is we wrap it with this my context run and the lambda calling throw, and then we can sleep, do whatever else, and ultimately we can just do try catch and wait for it the way we like, and the exception will be propagated and swallowed here. So you can see that it did happen, it didn't kill our application, it did work, and it did print out the exception. So this is obviously a hack, a big hack, but now we understand all these things and we can just re-implement all the details to await async void methods. To summarize, know your synchronization context and do not abuse it. Do not use async void, use async all the way up, use configure await false all the way down. Do not create threads manually and all that stuff. And also always wait for your tasks to not lose the exceptions. If you would like to read more about these things, couple books I highly recommend for you to read. A couple links to my blog explaining more of what we did today. Couple links to the open internet to read about all these internals, etc. And having said all of that, we can now move on to Q&A. I'd like to thank you for attending this talk. This is the QR code for the slide deck. And now, let's go to the Q&A. Okay, so I do see questions. How would you debug async state machine code? It's generally hard and simple. Like conceptually, it's simple. You either use the memory dumps or you use .NET Spy, DN Spy application. So you can easily step through all these things. What is hard about this thing is that it's much harder to track the stack traces and callbacks, how they are connected between the threads, because your continuation may switch threads, so you lose the call stacks. And it's generally hard to understand how these things work under the hood if you do not remember all the details. There is a very nice talk by Kevin Gose and Christoph Nassar, I believe from NDC like last year or NDC Oslo this year. They show how to recreate the stack call stacks from the tasks just by using like memory dumps and going through the codes. Highly recommend taking a look at them. But the answer is conceptually it's simple. You just need to create the call stacks, recreate the call stacks, but technically it's very hard because you need to go through a lot of technical internal state, all these like state fields, etc. And typically it takes a lot of time. But there are tools. WinDBG, DN Spy are the most useful for you, and at the talk I mentioned. Another question. Usually when we use async and await, we already use the methods provided by the library. For example, we use await SQL reader, SQL data reader, read async to read the data from the database. Asynchronously, what if you need to write a truly asynchronous method yourself that does not block the thread? Do you know how these methods are implemented under the hood and how they work? That depends. For instance, task delay, it works just by creating a new timer, and this new timer ultimately calls the the complete on the task. The typical pattern here, how you implement this is you use task completion source. This task completion source has a method like complete or set result, something like this. And this set result you call when you are done. Now, how you get to this set result call, it depends on the machinery you are doing, right? If you are waiting, like calculating something, just call this method explicitly after calculation. If you are waiting using some other asynchronous patterns, like just schedule the continuation on some EAP or on some background callback, which will call this method for you. If you are doing some IO, truly IO work, which you probably don't because we just use the methods for that. But if you do that, then you use IO completion ports, and once everything is done, you just call the set result on the completion source. So this is the pattern how you do it. Task completion source, you return task from it to the caller, and you call set result on the task completion source at your convenience when you are done, when you are ready. This is how these things are implemented. Now, the only question is how you get to this set result call and what triggers it. Okay, actually, if you would like to check these things, it's super easy to now open the source code of, for instance, task delay method or reference sources or GitHub, whatever, and see how they work. I have another question. I have recently heard the .NET interview question. What is the major benefit of using async and await ASP.NET Core controller? How would you answer it? The benefit is because we do not block the thread. One thread can handle multiple requests. Initially, the web applications, the way they worked, not only in .NET, but generally in the IT, was that we wait on the socket for the connection, and then we create new thread and give it the connection to handle. So each connection required one thread. However, now, because the thread is not blocked, it can go and grab another connection and start handling it. So one thread may handle multiple connections, multiple network calls. And that's the whole point of async and await in ASP.NET Core applications. Then one thread handles multiple network calls. That's the benefit. And obviously the outcomes of that are pretty clear. Lower memory usage, fewer threads, fewer scheduling issues, yada, yada. But everything comes from this principle, never block the operating system thread. Okay, I do not see any other questions. So I believe that would be it for the talk. It was slightly longer than we expected. So I'd like to thank you